Hey, welcome to high school chemistry. My name is Rex. Today we're going to be studying separation techniques. But before we do that, we're going to talk about the properties and differences of matter, elements, compounds, and mixtures, and then we're going to talk about the difference between compounds and mixtures. Matter is anything that has mass or takes up space. So practically, everything around us is matter. How do we know the different properties of matter, such as its hardness, its size, its pH value, its flammability, toxicity, and so on? These are grouped into two properties of matter. They are the physical properties and then the chemical properties. The physical properties of matter are those that can be classified, identified, and described without having to change the chemical identity of the object or substance. So I'm talking about size, shape, basically things we can see: hardness, volume, density, luster, electric conductivity, and so on. But chemical properties of matter have to do with the chemical identity of the substance and how it can react with different substances. These include solubility, flammability, toxicity, and so on. From these physical and chemical properties, we're going to learn about physical and chemical changes. So I'm going to write down their differences because that's what we're going to talk about. Physical and then chemical changes. Basically, physical and chemical changes are just the change in physical or chemical properties. So the first difference between physical change and chemical change is that physical change can be reversed, while chemical changes cannot be reversed. The next difference between physical changes and chemical changes is that physical changes don't require a lot of heat, while chemical changes require lots of heat. And the third difference between physical and chemical changes is that when physical changes occur, no new substances are formed. But when it comes to chemical changes, new substances are formed. Okay, now from these differences, I'm going to give different examples, or I'm going to give at least one example for physical change and chemical change. An example of physical change is a salt solution. A salt solution is practically just salt and water together. So it's an experiment you can actually do at home. Just get a bowl, pour some water, pour some salt, and stir, and now you have a salt solution. A solution is usually gotten from a solute and a solvent. A solute is the solid in the solution, and the solvent is the liquid in the solution. So in this case, the solute is salt, and the solvent is water. So can salt solution be reversed? Like the chemical change we just went through by mixing salt and water together, can it be reversed? Yes, it can. All you need to do is evaporate the salt solution, and then you have your salt and water. We're going to talk about that in separation techniques. It doesn't require a lot of heat, of course. What we didn't even require any heat at all. And number three, no new substances were formed. Of course, no substances were formed. The only thing that was formed was the word solution. No new substances were formed. It was practically just salt and water in a solution. And when it comes to chemical changes, an example is the burning of wood. Can the burning of wood be reversed? Of course, the burning of wood cannot be reversed. When wood is burnt, it yields ashes and gases. And you can't bring ashes and gases back to form wood unless you did playback, which is not possible. Need for lots of heat. Well, yes, to burn wood, you need a lot of heat. You need a fire to burn wood to be able to yield the ashes and the gases. And are new substances formed? Yes, they are. New substances are formed from the wood separating into ashes and gases after the chemical reaction of burning. So I've talked about the differences between physical and chemical change. Next, we're going to learn about elements, compounds, and mixtures. What is an element? An element is the simplest unit of a substance, which cannot be divided into any simpler units by an ordinary chemical process. Now, what I just explained means that I need to explain one term when it comes to matter and properties of matter to be able to understand elements. Matter is made up of basic building blocks called atoms. Atoms is derived from the Greek word atomos, which means indivisible. And it was believed for a long time that the atom was indivisible. It's like saying if I brought this marker and I divided it in half, and I brought one half and divided it into another half, and I brought the other half and divided it into halves, and I kept on dividing it until I could no longer divide it, then we ended up with an atom. And it was correct until the late 1900s, when it was discovered that yes, the atom was actually divisible, and it yielded subparticles, three, which are called the electron, which has a negative charge, the proton, which has a positive charge, and then the neutron, which has a zero charge. That means the neutron is neutral. All right? And these are the three subparticles that consist of the atom. You don't have to memorize any of these names or their properties. All you need to keep in mind is the word proton. Okay? The electron and neutron will come in later when we're talking about atoms in chemistry. But keep the word proton. An element is the simplest unit of a substance, whereas an atom is the simplest unit of matter. What is the difference between these two terms? Because they're both simple units of something. Well, you have to keep in mind that an element consists of atoms of the same protons. That's why I said you should keep the word proton in mind. An element has its name from the different number of protons the atom has. So I'm going to list out for you 10 elements before I continue my explanation, or I'm going to give you at least 5. So there's hydrogen, there's helium, there's lithium, there's beryllium, and there's boron. All right, these are all elements, okay? And these all consist of atoms of the same protons. The proton of an atom that an element consists of is also known as the element's atomic number. It's the number that if you go to the periodic table, you can easily use to identify the element without having to start searching all the letters. So hydrogen has an atomic number of 1. Helium has an atomic number of 2. Lithium has an atomic number of 3. Beryllium has an atomic number of 4, and boron has an atomic number of 5. This means that the atoms of hydrogen have 1 proton in their nucleus. That's what it's called. And the atom of helium has 2 protons in its nucleus. Atom of lithium has 3 protons in its nucleus. Beryllium has 4 atoms. The beryllium atom has 4 protons in its nucleus, and the boron atom has 5 protons in its nucleus. These are all elements, like I said. So an element of hydrogen consists of similar hydrogen atoms made of the same protons. An element of helium consists of different helium atoms of the same protons, which are 2, 1, 3, 4, and 5. Also remember that the number of protons that an atom has, which an element consists of, is the atomic number of the element. Before we dive into compounds, I want to tell you how to identify different elements on the periodic table, at least for beginners, before we jump into the periodic table in later topics. So let me clean this up. There are different types of elements. There's the metals, there's the submetals or metalloids, and then there's the nonmetals. The elements that are metals are practically the ones that have the metallic properties, both physical and chemical. An example is iron, gold, copper, tin, zinc, and so on. The metalloids are the group of elements that show some metallic properties, but also show some non-metallic properties. And nonmetals are those elements that show non-metallic properties, both physical and chemical. There's carbon, nitrogen, oxygen, fluorine, chlorine, and so much more. I want to write out the differences between nonmetals and metals. We're going to learn about the physical properties, and then we're going to learn about the chemical properties. So here's metals and nonmetals. Right? I won't be able to write it down, so I don't, take a lot of time. The first difference between metals and nonmetals, that's the physical properties, is metals are sonorous, ductile, and malleable. Ductile means that they can be bent into wires. Malleable means that they can be hammered without breaking or losing their shape. And then sonorous means that they can make loud noises. Nonmetals are not ductile, malleable, or even sonorous. Another difference between metals and nonmetals is that metals have tensile strength. They're very strong. and they have high melting and boiling points. But nonmetals don't have any tensile strength. They can easily break. It means that they're brittle, and they have low boiling points or low melting points. It means it's not difficult to heat them and they can melt. But it's very difficult for you to heat metals, and you have to heat them to a very high temperature. That's what happens in armories when they have to heat up metals to become lava, and then they can shape them into different objects when they cool. Another difference between metals and nonmetals is that metals are good conductors of electricity and heat. It means they can conduct electricity easily. Nonmetals are insulators. It means that they can't conduct electricity or heat very easily. The last difference between metals and nonmetals is that metals have a high density. It means that they can sink in anything or any liquid that has a lower density than the metals. And the most common thing that is less dense than any metal is water. Most metals don't float on water. This is because they are less dense than water. But anything non-metal is less dense than water. That's why they float. Non-metals, which include plastic, wood, rubber, and so on, are less dense than water. That's why they float. We've discussed the difference between metals and nonmetals in a physical level. Now let's get to the chemical level. These are the parts we usually have to focus on when we're talking about chemical reactions. So, metals and nonmetals. By the way, I forgot to ask you, in the physical differences between metals and nonmetals, which one did you prefer? Did you prefer the sonorous, ductile, and the tensile strength metals? Or did you prefer the free, loose, and even floaty nonmetals? Let me know in the comments. Anyway, we're talking about the chemical properties of metals and nonmetals. The first chemical difference between metals and nonmetals is that metals usually ionize by releasing one electron and passing it to another element, while nonmetals receive electrons from another element to themselves. We're going to discuss about this when we're talking about atoms, but just keep that in mind. The next difference between metals and nonmetals is that metals combine with oxygen to form basic oxides, but nonmetals combine with oxygen to form acidic oxides. Don't worry, you don't have to understand that for now. The last difference between metals and nonmetals is that metals combine with other elements in a way that is called ionic combination, but nonmetals combine with other elements in a way that is called covalent combination. And finally, we can dive into separation techniques. So you already know that what we've been studying is to prepare us for the main topic, which is separation techniques. Now that we know the different properties of matter, both chemical and physical, sometimes different matter, both elements or substances and compounds, can be mixed together, and we want to separate them. That is where separation techniques come in. Before we learn about separation techniques, I want us to learn a few terms. Solute, which we already talked about, solvent, immiscible, mixable, soluble, and insoluble. A solute, like I said before, is the solid in a solution. The solvent is the liquid in the solution. Mixable is between two liquids, when those two liquids cannot be mixed together. An example is oil and water or petrol and water. If you pour water and then you pour petrol, you'll notice that petrol forms a layer on top of the water. Do you want to know why? This is because petrol is less dense than water. Remember that anything that floats on top of another liquid means it is less dense. Mixable is between two liquids when these two liquids can be mixed together to form a new solution. An example is soda and water. Then insoluble means a solid that cannot be dissolved in a solution. An example is sand. Sand cannot be dissolved in water. If you pour sand in water, it's just going to form a clear layer of water and then a layer of sand at the bottom. And lastly, soluble means a solid that can dissolve in a solvent or in a liquid. An example is salt and water. If you pour salt in water and stir it, you're going to get a dissolved salt solution. As I've explained these terms, we're going to group some of these separation techniques based on the terms I mentioned. How to separate solids of different sizes, sieving. How to separate magnetic solids from non-magnetic solids, you have magnetic separation. How to separate a sublimable solid from a non-sublimable solid is sublimation. And then, how to separate an insoluble solid from a liquid. This means if you want to separate something like sand and water, you have three options. filtration, filtration, decantation, decantation, or centrifugation. Let's explain these terms. Sieving, like I said, sieving is used to separate solids of different sizes. You already know what a sieve looks like. So here's an example. If I was a clay potter and I asked someone to get me some clay, and the person got me clay, and you know the clay contains some impurities like stones, shells, and things like that. I want to separate the clay, but I wouldn't start picking out all the stones one by one, plus the shells and all of that stuff. So what am I going to do? I'm going to use a sieve to separate the clay from the impurities like the stones and other impurities. So in the laboratory, we use a group of sieves that are arranged in descending order, from the biggest sieve to the smallest sieve. So I would just pour the clay inside and shake the sieve, and the sieve would pour the clay with some other impurities that could pass through the apertures of the sieve. The apertures are those little holes in the sieve, and the diameter of the apertures allows whatever solid that is smaller than the aperture to pass through it. Since we're talking about the big sieves, they would have big apertures that would allow clay to pass through, plus some other impurities that might be smaller than the apertures, and would just be sieving in descending order until we reach the smallest sieve, where we can now get the clay without all those impurities. That's an example of sieving. Next is magnetic separation. So here's a very funny example. Let's just say your mom was cooking in the kitchen, and then you just brought some iron filings, and then you pour them in your mother's pot of what she's cooking. So first of all, I don't even know how you got there. I don't even know how the iron filings got there, but let's just use that as an example. And then you start panicking. Well, if I were you, I wouldn't start panicking. What we would do is use magnetic separation. Before I explain magnetic separation, I'd like to tell you that metals, which I talked about as elements, can either be grouped into paramagnetic or ferromagnetic metals. Ferromagnetic metals are those metals that can be strongly attracted to a magnet. But paramagnetic metals are those metals that can be attracted to a magnet, but not as strong as ferromagnetic metals. Some examples of ferromagnetic metals are iron, nickel, and tin. Some examples of paramagnetic metals are lithium and aluminium. So let's just say I poured iron filings. Sorry, let's say you poured iron filings into the pot. And so you just bring a magnet and, put it over the pot, and then the iron filings will be attracted to the magnet. Because remember, iron is ferromagnetic. And so they would be attracted out of the pot, and then you have your mother's pot of food. But I advise, caution, do not go do that, because I tried that once and it didn't really go successfully. First of all, the iron filings might have already cooked up with the food, and then you wouldn't be able to separate the iron filings because you would also get out the iron filings plus the food. So I just advise that you don't do that. Better safe than sorry. Anyway, the next is sublimation. Sublimation has to do with sublimable materials from non-sublimable ones. First of all, what does it mean to sublime? Let me clean off these. I should have explained this at the beginning of the lesson, but it's okay, we're going to learn it here. So, you know the three forms of matter: solids, liquids, and gases. These three forms of matter can transition from one form to another form to another form. So in chemistry, we use something called the forms of matter triangle, as I like to call it. So let's say this is a gas. Let's say this is a solid. Sorry, not solid. Let's say this is a solid. And let's say this is a liquid. All right? A solid can transition to a liquid by melting. A liquid can transition to a solid by freezing. A liquid can transition to a gas by evaporation. Evaporation. And then a gas can transition back to a liquid by condensation. Just say condense. Now, what about solid to gas? If I knew that solid wasn't going to transition to gas directly, which is actually usually the case for most substances, why did I have to draw this triangle? Well, it's because I know that there are some special substances that can go from solid to gas directly, and that is known as sublimation, both forward and backward. So to go from solid to gas is sublimation, and to go from gas to solid is still sublimation. It's sublime. Some examples of these substances are camphor and dry ice, which is actually carbon 4 oxide, but in solid form. So let me clean off this forms of matter triangle. forms of matter triangle. And I'll write down the separation techniques we're currently talking about, and that is sublimation. So how do we separate sublimable materials from non-sublimable materials? Let's say we mix camphor with salt. Note, if you're going to follow this step, whatever substance you mix it with must not decompose on heating. What do I mean? Something like salt and sugar are not the same, right? Salt does not decompose on heating. This is because of the strength between the sodium and chlorine ions. No matter how long you heat them, day and night, they're not going to decompose. It's still going to remain that strong bond of sodium chloride or table salt. Sugar, on the other hand, decomposes on heating to yield sugar caramel and then sugar charcoal and ash and stuff like that. So sugar decomposes on heating, but salt does not. That's why I used an example of salt. Whatever substance was mixed with the sublimable material must not decompose on heating. So let's say you mix camphor with salt or carbon 4 oxide with salt. You can use sublimation because carbon 4 oxide sublimes on heating. So let's say this is my dish and I just got, carbon 4 oxide and some salt. On heating it, all right, the carbon 4 oxide is going to sublime out of this mixture, and then you're going to be left with just salt. That is a good way to think about it. Kind of a safe way. And lastly, I want to talk about these three last groups of how to separate insoluble solids from their mixtures. From solvents. So I'm going to talk about filtration first. Filtration involves the use of a special type of paper called filter paper. It's folded into a cone and then placed in a funnel, and then whatever solution you have that contains an insoluble solid can be poured in through the filter paper. So let's use that water and sand. Sand cannot dissolve in water. It means sand is insoluble. So if I pour water and sand into that filter paper that contains into the funnel that contains filter paper, you're going to be left with only sand as the residue, and then you're going to be left with the filtrate, which is water. The filtrate is the liquid or the solvent that passes through the funnel, and then the residue is what is left at the top. So sand is the residue, and the filtrate is water. When it comes to decantation is a method that is not advised by any scientist because it was a method used by our ancient fathers, but it's not really safe or it's not really precise when it comes to separating different substances, or particularly separating insoluble solids from their solvents. What is decantation? If maybe it's raining and then you want to get some water from rain, and you know that rainwater comes with some impurities like dirt, and let's say rain goes into whatever container you placed outside for rain to get in, and then you see that there's some impurities that settle at the bottom. For instance, let's use that sand and water again. Sand and water is a very good example of an insoluble solid and a solvent. So the decantation involves let's say this is the beaker containing sand and water. So let's say this is water. Like I said, it will create a clear layer of sand at the bottom. So decantation involves you pouring the water into another container that is waiting for you to pour the water into it, and it involves you pouring the water into the container because the sand forms a clear layer at the bottom. But the reason why I said this isn't advisable is because some molecules of the sand will still follow the water into the bowl. And this is not an accurate method of separating insoluble solids from solvents, because when a molecule of sand follows the water, it might affect its chemical properties. Remember what I talked about, chemical and physical properties. Decantation is the worst, and it's not advised that you follow this method. It's actually just taught so you can know that there's another method that is used for separating insoluble solids from solvents. The last is centrifugation. I want you to do some research and tell me your findings in the comments. And now for the questions. Actually, this is the first question. So the second question is, can you give me 3 more elements or 4 more elements from the periodic table apart from the ones I mentioned in this class? There are about 118 elements, so do some research and tell me in the comments. If you enjoyed this video, please like, subscribe, and share with at least 3 people you know don't have access to basic education or who is bold enough to explore homeschool. And I'll see you in the next class.